There we go. Okay, so the problem here would be, if you look ahead, because there's no variable that's easy to isolate, I would get a fraction. And it's not like that prevents me from doing it, but it's inconvenient, right? So this might be a good candidate for doing something else. Right, what is the something else that, remember?
Elimination.
Elimination, right. So elimination, and here are the steps for elimination. Here's kind of a way to think about it. Okay, this is the way, this is pretty standard out of a textbook. I'm going to make one little tweak to this that I think is helpful. I mean, you're welcome to do it whichever way you want, but typically what you're told to do with elimination is you line up the equations, you multiply one or both equations, by some constant, some number. Okay, I'm going to wait here. You ready?
We have to substitute.
Yeah.
Yeah, is there a different assignment?
Oh, you guys don't have that one.
Yeah, we have a substitution.
You don't have that one,
You can
okay.
Just copy it. Copy it down.
And
Just,
write
I'll tell you what,
elimination.
I don't, is it over?
If it's not, it doesn't.
This will roll. Yeah, don't, you know what, I think I might have left it in the copy room. You just copy it down, it's not a big deal, it's just gonna be this little list. I'll put this up online too, so these PDFs will be up online, okay?
Thank you.
So, we line up the equations, we're gonna multiply one or both equations by some number, and here's the key. We want it to result in a variable with the same coefficient. Actually, and what I'm gonna say, we want it to result in a variable with opposite coefficients. But let's go through this first, and then we'll improve this a little bit. I'm gonna go to another slide that's just like this with a couple tweaks. So maybe you wanna wait just a second before you write too much down anyway. It says add or subtract the equations to eliminate that variable, and then solve for the remaining variable, right? And substitute back. Okay, but here's an improvement. This is a better way to do it, I think. I think it's more consistent with things you're gonna do later on in linear algebra, like if you do linear algebra in college with bigger systems. This is a better way to think about it. You want to multiply one or both equations by a number to result in a variable with opposite coefficients. Okay? So when we add these things up then, and instead of subtracting, we're always going to add the equations to cancel the variable. Okay? And then that leaves us with a simple equation that we can solve for that variable, which we substitute back into one of the original equations to find the other one. Okay, that's a lot of steps to think ahead about. Let's look at an example. We'll go through it step by step. We'll look at a couple examples. Okay, so how about this guy right here? So first of all, those almost work, don't they? Now I could just subtract those equations. The problem with subtracting the equations is people tend to make mistakes. If I get, like when we work with bigger linear systems that have 4 or 5 variables in them instead of just 2, when you're subtracting, it's really easy to make a mistake subtracting, to forget to distribute that negative and subtract. It happens all the time. It's just human nature. It's a tricky thing to do. And so what I would recommend we do instead is we multiply one of those equations by what? By -1, right? To make the x negative in one of them and positive in the other. So then when we add vertically, the x's will cancel, right? So how would we show that? Well, there's a bunch of ways to do it. I think a way that's not bad is to go like this, is to just, whatever I'm going to multiply one of the equations by, I'm going to put it outside the brackets. Eric, go ahead. Hey, I'm in classes. Can I get you back in just a little bit? No, I get you an updated one. It's a little better. Yeah, okay. Bye. Okay. So I'm just going to distribute a negative through that, right? And what's that going to give us? The top equation is going to stay the same. So we'll rewrite the system. The bottom equation is going to become, I got to distribute the negative all the way through, so it just changes all the signs. And now all I do is add vertically. What happens? The x's cancel. Good. So the x's cancel. and we end up with 8y equals 10. Oh, whoops, you're right, positive 7. Yep. So 8y equals 24. There you go, okay? So if I divide by 8, what do I get? Okay, so y equals 3. There's half of my solution, but I need an x value too, right? So where do I go to get the x value? Plug it into any of the, and typically it's better to go back to the original equations because a lot of times I've multiplied by something to get bigger, and I've got bigger coefficients here. So go back to whichever one of the original equations is most convenient. Doesn't matter. So let's just take the bottom one, how about? So if we use the original bottom equation and we plug in y equals 3, we just get x minus 3 equals negative 7. So what's x? Negative 4. And so we end up then with the solution negative 4, 3.
Wait. Oh. next one.
Okay, does that make sense? Do you remember doing this stuff? It's been a while.
I thought we did it last time.
You would have done it. You would have done it in Algebra 1. You would have done a fair amount of this in Algebra 1. Okay, so let's do another one here. So I'm going to show you another way of doing the work, and I don't care. You can take your pick. This is I'll show you the way I typically have done it. This is more consistent with the solutions that are going to be published, the way I did it up here. But I'll show you another way that I kind of like. What do I need to do here? Which variable is going to be convenient to cancel? The bottom one, right? The x. Okay, so what do we need to multiply through on both sides of the bottom? Negative 4. Okay, so here's kind of a slick way of doing this. I could go the top one, I'm going to make an arrow, and if I multiply by anything, I'm just going to put a little bubble in the arrow that tells me what I'm distributing through both sides. Okay, take it or leave. They're just little ways of showing it. So this one's going to stay the same. It's going to be 4x minus 9y equals negative 42. The bottom one, you told me to multiply by negative 4, so what's it going to become? Okay, so then those guys cancel, right? Yeah, whichever one's most convenient. We'd like to, and what's it mean to be most convenient? We want to multiply by the smallest number and the least number of constants. Like I could have multiplied the top by 5 and the bottom by negative 9, but why, right? Made the y's cancel. That'd make things excessively complicated, right? We could make this very simple by just canceling the x's in this case. So when we add those up, what do we get? Negative 29y equals negative 58. So what's y? 2. If y equals 2, how about if we plug back into that bottom equation? It's got small coefficients. And so then we'll get x plus 5 times 2.
So x
4.
is negative 6.
So x is negative 6. Exactly. Okay, and so we get the solution negative 6, 2. What do you think? First or second method? You take your pick. Either one, right? Okay, so what about one like this? Let's just do one that's a little bit tougher. Now, take a second. This one you want to contemplate for just a second. It's not like there's any dramatically right or wrong answer here, but I'd say there's one that's a little better. You're right. So what do you have to do? What do you think, Dean? Multiply both of them. So what do you think? Which variable would be slightly better to probably eliminate? X. Yeah, right, because the x's I can multiply by smaller things, right? Okay, so what are we going to multiply the top equation by?
2.
Okay, so if we pick 2 for the top one, what do we want to pick for the bottom one? Negative 5. Okay, and that works great because then we're gonna get a 10x plus 6y equals negative 14. On the bottom, we get what? Negative 10x minus 35y equals negative 15. Did I do that right?
Yeah.
Okay. So the x's cancel, and we get negative 20, is that 29? 29y equals negative 29, and so y equals 1. And then we'll plug back into either one, doesn't matter. How about if we plug into top one there? So 5x plus 3 times negative 1 is negative 7. What's 5x equal to?
Which is
Wait.
just
Did I mess that up?
negative one.
Oh, positive. So I get, all right, yeah. Okay, so I get 5x plus 3 equals
So X
negative
is
7.
negative.
So x equals.
Yeah, right, I'm gonna get 5x equals negative 10, so x is negative 2. There's my solution. We want to write it as an ordered pair.
Do you always do that?
Yeah. Okay? All right, so there's, that should be, you've done all that stuff, right? Okay?
Sure.
So there's another analytical technique, another way we can algebraically solve systems. Okay, so what I want to end up with here then today, I want to look at some typical kinds of applications, right? Types of problems that are well suited for a linear system. Okay, so how are we going to do this? We always, when we're looking at any kind of a word problem, and especially when we start getting into systems word problems, where there's a little bit more going on, we always want to define our variables. Every time we got to write down, the first thing you should always do is write down what are your variables going to be, because then that makes it a lot easier to set up the equations, okay? So we set up the equations and we're going to solve the system. So take a second and just everybody read through this. And I think it's a good idea to read through it twice. I think you read through it once to kind of get a feel for it, then you read through it again for more, be a little more specific. So what do you think? What are the variables? Okay, the babysitting and water park hours? No? Okay, yeah, it's like his hourly wage at each job. How do you, and you can cheat on this one, how do you know? How do you know what the variables are? Yeah, but there's even a quicker way, just like a foolproof way to find out what the unknowns are when you're solving a word problem.
When they change. Oh.
Look at the question.
Pretty obvious.
Right? I mean, this would be a pretty dumb question if I gave you all that information and I said, how many hours did Landon work at the water park the first week? Well, it's 10, right? I mean, it's not an unknown, it's a known, they gave it to you. How much did Landon make combined the second week? Well, $177 right there, it's not an unknown. You don't have to know too much math to be able to find that information, right? But invariably, if they're gonna ask you a question about it, if we're doing something meaningful, you're trying to find something that's not given to us. And so whatever's being asked in the question is always gonna be, those are gonna be represent the unknowns, right? So it asks you, how much does Landon make per hour at each job? There you go. Those are the unknowns. We call them whatever you want. Let's say B is for babysitting wage. And let's say W is for, I'm just gonna call it water wage. Okay, so the hourly wage, how much is he making per hour at those two jobs? So now we've got to try to turn this into some equations. Okay, so 1 week he babysat for 3 hours and worked at the water park for 10 hours and made $109. So how could I set up an equation that represents that first piece of information? Okay, everybody see that? Right? So the blue sentence is just telling us 3B plus 10W equals 109, right? Doesn't that make sense? The number, and if I'm calculating a babysitting wage, think what a babysitting wage is gonna be. It's gonna be in like dollars per hour or something, right? Or, yeah, dollars per hour, right? Does that make sense? So the units for this are dollars per hour. Units for water wage, dollars per hour. So 3 hours times B dollars per hour tells us dollars, doesn't it? That make sense? Can you see how those units work there? That's it. That dimensional analysis works. It's great in math and science, right? You know you're looking at the right kind of thing if the units give you what you expect. So I'm multiplying hours times dollars per hour. The hours cancel and I get dollars. We're on track then. So this is the amount of money from babysitting. This is the amount of money from the water park, and it adds up to 109. So then how would I say next week babysat for 8 hours and worked at the water park for 12 hours and made 177?
A equals 12, W equals 177.
That was pretty good. Did you practice that? And so there's our linear system, right? And now that's just stuff we're doing. Right? Now we can solve that probably using elimination, okay? And then we'll talk about, well, yeah, I mean, we can solve that using elimination, or if we wanted to maybe use technology, what could we do? Yeah. Graph them both and find the point of intersection, okay? If we had technology available. And we don't even have to maybe finish that problem, but that's how we set it up, right? That make sense? Okay? All right. How about something like this? Okay, read that one. What do you think? What are the variables? Number of pennies and number of nickels. He wants to know how many coins of each type does Kent have here. So we got P equals, we'll call it P, how about? P equals number of pennies and nickels. N equals number of nickels, right? So how would I say this first sentence then. Yes, collection of pennies and nickels with a value of $1.98.
P plus 0.05 n equals 1 per penny.
Okay, good, so we need the value of the pennies plus the value of the nickels equals the total value, right? That makes sense? So the value of the pennies would just be 0.01 p. Everybody agree? There's one, it's, excuse me, $0.01 times the number of pennies tells us how many dollars worth of pennies we have. So this is, we could summarize that as value of pennies plus, how would I say the values of the nickels then?
0.05.
And what's it equal? And that's total value. So there's one equation. Is that enough, by the way? How come? Okay, we got more information, but I need more information, don't I? Because how many unknowns are there in that equation? Two. And how many equations do we need then? Two, right? Have we mentioned that at all? Yeah. Okay, good. Thought so. Well, I'll probably say that a bunch of times this year, because that's a fundamental thing about very important stuff. You always have to have at least as many unique equations as you have unknowns in the system to solve for, right? So we got to have at least one more equation, and they give us one. 5 less than twice the number of nickels, right? Yes. 5 less than twice the number of nickels. Got the number of pennies he has. Number of pennies is 5 less than twice the number of nickels. Okay, so how am I going to say that one? Okay, does this deal with value at all here?
No, just the number.
Just the number, right? So I don't really need those rates in there, right? I don't really need just the numbers of pennies and the number of nickels, and that's what P and N stand for, right? So the number of pennies he has is, well, what's that tell us? So that's telling us P is means equals, right? And then 5 less than twice the number of nickels. There you go. Okay? So the last example we looked at was an example where we would want to use linear combination, isn't it? Right?
Yeah.
You notice that the examples when we want to use linear combination are in standard form, right? When we represent, like in your futures, I'm assuming many of you are going to go on and do a lot more math. In your futures, when you do something like a linear algebra and matrix theory class in college, right? You're going to study how to deal with very large linear systems. And now we can use technology to do it pretty easily. But there's some other, besides just solving systems, there's some other parts of that. You'll notice though, when you talk about big linear systems, you always want to write the linear systems in standard form. And you'll get a little sense of that. I'm going to show you guys some things that are kind of outside of the textbook here. They're sort of high level things, and you'll see that in action. Well, I'll show you ways to solve using technology to solve some big linear systems that would take you hours to do without technology. You can do it really quickly with technology. This one, though, this system is set up for what? Substitution. Look, there's your substitution equation right there. Right? Now, we could put this in standard form and use linear combination, but this one's set up for substitution, isn't it? So there's our system. We would just substitute the P in there and solve for N. Once I find N, I go back to my boxed substitution equation and plug it in to find P. Make sense? Okay? All right. I'm prepared to let you work here. When are we out of here?
10.
Okay. I'm prepared to let you work. Do you want a little... I've got a pretty good puzzler if you want one.